Hey guys, it's Mr. Ray here with our next calculus lesson. We're going to continue on with learning new techniques to take derivatives. Uh, Last lesson we looked at polynomial functions and any kind of function that had any kind of rational or negative integer or positive integer exponents. So that covers quite a bit of territory, but there's lots of other functions, types of functions that we need to explore. So today we're looking at the derivatives of composite functions. So um, uh, before we get to that, just a reminder, the derivative is a mathematical function which gives the slope of a tangent at a point along a given function, or it could be considered to give the instantaneous rate of change at a given value or given point. Okay, both of them mean the same thing. Slope of the tangent, instantaneous rate of change, and derivative all mean the same thing. So now we're speaking in terms of that as the derivative, because the derivative is a function. Okay, um, so composite function. The composite function, if you remember from probably the last unit in advanced functions, uh, may have skipped over this pretty quick, depending on how much time you had to learn the course. Actually, I think we learned it in grade 11 too. So just a reminder, basically a composite function is a function of a function, okay? So I've got the definition here. This is kind of the terminology. We could say that, we could say a composite function if we have two functions, f and g. Composite function, we could refer to it FOG, or I don't usually use this, or this, FOG of x. Uh, the terminology I prefer is f of g of x. So we talk about g of x as being the inside function and f as being the outside function. So the way we can kind of draw a picture of how that works, we've got these two functions. Now, the first function that gets used would be the inside function. So if we call this box, or this function g, and this function f, what happens is the function g gets fed the input x, and I didn't leave a lot of room here, but the output of the function g using input x is g of x. So g of x becomes the input into this next function f, so the output of that is f of g of x. Okay, or written in terms like that. So basically, you know, the order is important here, as you'll see later. But we first give the input into function g. G does its thing, evaluates what the function g at that value, spits out the output g of x. That becomes the input to f, and then you have the output of f, which is f of g of x. Okay. So the actual name of the rule that we use for derivatives of composite functions is called the chain rule. So that's probably the terminology you'll hear most about this lesson. It's learning how to use the chain rule. So in this case, if y is a function of u and u is a function of x, so you've got your function of a function, composite function, then now we've seen this already. We used that for dy by dx. So if you have two different functions, you could almost do you do two separate derivatives in the case where you have the two functions. So the first derivative here, you basically the derivative of y with respect to u, that's what that means, times the derivative of u with respect to x. So it's this double derivative, and you multiply the results. Okay. Now you could almost think of this as a fraction here. Now it's not really a fraction, but it works out the same because you've got a du and a du on the bottom and a du on the top. So it's almost like you can cancel them out. and you're left with dy by dx, which is what you're trying to get. Okay, so it's not a bad way to remember it when you're doing this. Now, obviously, you can only do dy by dx if these two separate derivatives exist. Okay. Now, this is kind of a very complicated looking formula. So if h of x is f of g of x, I could again write it the way I just used it, then the derivative of h of x is equal to the derivative of f with respect to g of x times the derivative of g with respect to x. So it's a little bit complicated. It could be written this way as well. I just find it's kind of better to see a few examples before you try to apply it back to this. Okay. Now there's a special situation where if the outside function is just an exponent, like a power function, and we saw something like this in the last lesson, where we had like a binomial to an exponent. So you can't just do it the way you did it with polynomial rule. You could see. So what we're going to do here is now let's just skip this part here for a second. So if we're taking the derivative of, say, g of x to the power n, so what we do is we just pretend we're taking, like, this is just an x maybe. So that n, if it was just a power function, the n would come out front, and then multiply with g of x to the power n minus 1. So that's what really came from the polynomial rule. But since that inside function is not just x, it's some function of x, you have to multiply by the derivative of whatever that inside function is. So derivative of g of x. Okay, so we'll do some examples. It's not really that hard. It looks a little bit intimidating when you see all this it written in those forms. Okay, so let's do a bit of practice here with composite functions, just to remind ourselves how this works. Okay, so we have two functions. F of x is square root of x, and g of x is x plus 5. So we want to find these values. So this is stuff you've done in the past, but may or may not remember it. So the first thing we do is always evaluate the inside function. So they're actually giving us a value of the input. So g of 4 would be 4 plus 5. So that's really a 9 in the middle. So a becomes f of 9. And then we use that input 9 into the function f. So f of 9 would be square root of 9, which is equal to 3. Okay, the next one. We've got g of f of 4. So again, we're going to evaluate f of 4. F of 4 is the square root of 4, which is 2. So that simplifies to g of 2. So g of 2 would be 2 plus 5, which is 7. Okay. Oops, sorry. Couldn't see that one. So I'll just repeat that. F of 4 is square root of 4, so that's 2. So that becomes g of 2. Sorry, this becomes g of 2, and g of 2 is 2 plus 5, which is 7. Okay, and then we're going to actually, we're not using a value of x, we're kind of using the general formula here. But on the C, we've got f of g of x, and D, we've got g of f of x. So this is a good chance to see, are these two the same, or are they different? Okay, so the way we look at this is I'm just going to rewrite f of g of x, but I'm going to actually put the value of g of x inside the brackets. G of x is x plus 5. So I'm looking at what's f of x plus 5. So basically I go to the function f, and instead of using x as input, I'm using x plus 5. So the x plus 5 goes under the square root sign, and that will be f of g of x, the square root of x plus 5. Okay. Do the same thing with d, except that the functions are reversed in their order. So g is the outside function. F of x is actually square root of x, so it's g of square root of x. Okay, and now we go to the function g, and wherever we see an x, we're replacing it with square root of x. So the x just gets replaced with square root of x, and the plus 5 is outside. It's not under the square root this time. So these two are not the same. So f of g of x is not the same as g of f of x. And that's always, well, I guess there might be some situations where they could be the same, but as a rule, as a general rule, they don't have to be the same. In fact, most of the time they are completely different. Okay, so that's a good way of looking that the order is important. So it's not a commutative property where you can just change the order like multiplying and adding. You could think of this almost like subtracting or division where the order is important of what comes first and what comes second. Okay, so second page, we've got the formal definition of the chain rule. And we've seen that before. So basically we're looking at if f and g are functions that have derivatives, so they have to exist. Composite function h of x, which is f of g of x, has a derivative given by h prime of x, which is derivative of h. So it's the derivative of f of, it's the derivative of the function f with respect to g of x times the derivative of g with respect to x. Okay, so let's actually try this out. This will be where you can actually see what's going on. Okay, so here we do have a, you could think of this as, you know, I'll just do it for this one here. You could think of it as f of g of x. The g of x is the inside function. Let's see, so we've got x squared plus x to the 3/2. So the inner function, that would be your, so that would be your, like, call it g of x. That's x squared plus x. So that's the inside function. And then the outer function, which if we did in this order, that would be f. The outer function is equal to x, so something to the power 3/2. So in this case, x to the 3/2. So if I consider those as my as my inner and outer function, I know I'm going to need the derivative of both. So the derivative of g of x, so g prime of x, this is where you use your polynomial rule that we did the last lesson. So this would be 2 times x, and this would be 1. So 2x plus 1 is the derivative of g of x. And then let's see. So the second function is x is, what's the best way to say this? The derivative of f with respect to x would be 3/2 x to the 1/2. Okay, so we kind of put these together. So I just want to show you, thinking of these as inner and outer functions. So when I actually do my chain rule here, okay, the first thing I'm going to do is I'm going to use the, well, I'm going to use the outside function here. So this is going to be 3/2. And then whatever's in the inside, x squared plus x. And I'm going to reduce this by 1, or 2 over 2, so that becomes 1/2. And now the thing I have to do differently is now multiply by the derivative of g of x, the inside function. So the derivative of the inside function is 2x plus 1. Okay, Now, probably, you know, change that 1/2 now. You could change that to square root x squared plus x multiplied by 2x plus 1, and that would be your final version. Okay, I guess you could multiply the 3/2 into here, but that's not absolutely required in this case. I will be talking about how far do you have to simplify things. It's going to come out as a really important thing in a couple lessons from now when we do the next couple of rules. Okay, so we'll leave it like that. All right, so this next example, we're going to use the Leibniz notation, which is the dy by dx and etc. So if the function, if y is equal to u cubed minus 2u plus 1, where u is equal to 2 root x, find dy by dx at x equals 4. So if you remember dy by dx, now since this is a composite function, I can't differentiate y with respect to x at the moment because it's you know, the input variable is a u here. So the first thing I'm going to do is dy by du, okay, because I can take the derivative of this with respect to u, no problem. Okay, but then I'm going to get dy by dx, I have to multiply by du by dx. If you remember the fraction part here. So you could think of these as canceling out and you end up with dy by dx. And I can actually get dy by du, take the derivative of that with respect to u, take the derivative of u with respect to x. I can get those and multiply them together. Okay, so if I look at what's the derivative of y with respect to u, well, that's going to be 3u. I'm going to put these in brackets because I'm going to multiply this. 3u squared minus 2. And the derivative of 1 is 0, so that's dy by du there. And then now we're going to multiply by du by dx. So just to make this a little more obvious as to what I'm doing, I'm going to change the radical sign to an exponent. So that's going to be, well, it's 2 root x right now, which is the same as 2x to the 1/2. Okay, so if I'm taking the derivative of this with respect to x, okay, multiply the 1/2 with the 2, well, that becomes a 1. So that's a 1x, or just x. Now when I reduce the exponent by 1, remember I'm starting with 1/2, so 1/2 minus 1 is negative 1/2. So it changes into a negative exponent. And if you remember to convert that back, to radical form, that would be 1 over, to change it to positive, and then square root of x. So that is dy by dx. And we're finished, except for the fact that they don't want the general derivative, they want the derivative at x equals 4. So dy by dx at x equals 4 is equal to, and so one thing we have to do here, what do we do with the u here? Because what do I plug in for u? So this is where you actually so if I've got, just move this over here, if I've got 3u squared minus 2, I want to put this in terms of x. Okay, so I know u is equal to 2 root x, so this is equal to 3 times 2 root x squared. So I'm just replacing the u with 2 root x, and then subtract 2. Okay, so when I square this, you've got the 3 from before. The 2 squared becomes 4, and the square root of x squared becomes x. Right? So you got 3 times 4 times x, so that's 12x minus 2. Okay, so I'm now going to replace well, I won't plug in the x yet, but I'll just show you. You replace the 3u squared with 12x minus 2, and that's times 1 over root x from before. And now we plug in the 4. Okay, so we get 12 times 4 is 48, minus 2 is 46. And 1 over square root of 4 is 1/2. So that becomes 1/2 of 46, which is 23. Okay, so that's the derivative. That's dy by dx for x equals 4. Okay. So they may ask you the question, just like when we did slopes of find the slope of the tangent. Sometimes they want the general formula with just the x left in here, which would be this result, and sometimes they want it for a specific value of x. So once you've evaluated the derivative, you can just plug the x in at any time and simplify. Okay, so now we're going to use the chain rule. So this is a very important example. This is, you're going to see lots of functions that will have something like this in, y equals x squared minus 5 all to the power 7. Okay, so if we want dy by dx, okay, I'm going to do it the quicker way without using all the Leibniz formula in that. It's going to be, so this is the inside function. I'm going to take the derivative with respect to the inside function, so the 7 comes out in front and then multiplies with what's there already, but this time the power is 7 minus 1, which is 6. Okay, but now we also have to multiply this by the derivative of the inside function. So the derivative of x squared minus 5 is just 2x. So you shouldn't leave it like this, because you can very easily and make this look less complicated if you just multiply the 7 with the 2x. So that would be 14x x squared minus 5 to the power 6. And that would be the final answer. Definitely don't expand what's in the brackets. Okay, last page. Connecting the derivative to the slope of the tangent, because we already know those are the same things. So it says find the equation of the tangent for the graph of f of x equals 8 over x squared plus 4 at the value x equals 2. Okay, so you may have had this question last unit, like several lessons ago, but now we know we're just going to find the derivative of this, f of x, so we want f prime of x, and then substitute in x equals 2 to get the actual slope of the tangent, and then from that slope we can figure out what the equation of the tangent is. Okay, so first thing I'm going to do is just figure out, because I know I'm going to have to plug this point in to get the value of b later on. So that point, I know the x value is 2, they told us that, but if you plug in x equals 2 here, you get 8 over 2 squared plus 4. So 2 squared is 4, 4 plus 4. That would be the value 1, 8 over 8. So that's the point where we're going to use to get the equation of the tangent. Okay, so the first thing I'm going to do is I'm going to slightly rewrite f of x. Now, in a couple lessons from now, we'll actually have another rule we call the quotient rule, which is obviously division, where we'll figure out another way to do this. But for the time being, I'm just going to, you could consider that is 8 over x squared plus 4 to the power 1, but I could also bring that to the top and just change the exponent from positive 1 to negative 1. Okay, and this will be kind of a trick that you will be using quite a bit. So if I put negative 1 as the exponent, that basically means the same thing as this. Okay, and this is Sometimes desirable because you don't have to consider this to be like a division like this looks like, okay? All right, so now we're going to take the derivative of f of x, so f prime of x. So we're going to use the chain rule like we did before. Now that exponent is -1, so that comes out front, multiplies with the 8, so I get -8, and then the inside function is x squared plus 4. Okay, and now we reduce the -1 by 1, so that becomes -2. And we're not quite done yet. We still have to multiply by the derivative of the inside function, which is 2x. Okay, now we could simplify this. If it was just a derivative at any point, we would simplify this. But if we wanted to, we could just plug in f prime of 2 right now, just to save a line. So this becomes -8 times, and if I plug in the 2 here, that's 4 plus 4 is 8, and that's to the -2, which is, so this is really 1 over 8 squared times 2x, but x is 2, so that's times 4. Okay, so so I know this is going to be a fraction. So on the top I have -8 times 4, -32. On the bottom I have 8 squared. So that worked out nicely. So f prime of 2 is equal to -1/2 or -0.5. Okay, and we know the derivative is the slope of the tangent. So we could actually say this is our value of the slope, because we do need to create the equation. So this becomes fairly simple at this point. So the equation of the tangent is going to be y equals -0.5x plus b, and this is where we sub in the point 2, 1. So we've got 1 equals -0.5 times 2 plus b. -0.5 times 2, that's -1. Add 1 to both sides, we get b equals 2. And therefore the tangent's equation is y equals -0.5x plus 2. And that's what they were asking for, equation of the tangent at that point for that graph. Okay? So once you know what you're doing, we do these a few times, it becomes pretty routine. But you have to be careful. There's, even though there's not many lines there, there's a lot going on. Okay. Last example, 6 here, is it's a pretty interesting word problem, and it really shows you how think in terms of composite function. Okay, so let's read the problem and then we'll talk about that. Environmental study of a certain suburban community suggests that the average daily level of carbon monoxide in the air can be modeled by this function, C of P. C of P is parts per million of the carbon monoxide, and the input for this is the population of the community. Okay, so we use the population as input into this C function, which spits out the amount of carbon monoxide. Okay, and P is the population in thousands. It's estimated that T years from now, population of the community will be P of T is equal to 3.1 plus 0.1 T squared, 1,000 people. And now it's asking, at what rate will the carbon monoxide level be changing with respect to time? Okay, now this is important because we're wanting the rate of change of carbon monoxide with respect to time. And if you look at the carbon monoxide equation, it's not being measured with using time as the input. It's being measured with population as the input. Okay, so this is where the Leibniz notation is actually quite helpful. So they're asking, at what rate will the carbon monoxide level be changing with respect to time? So that's a derivative of C, or carbon monoxide, with respect to T. And since we don't have a function that uses t as an input and gives us c, this is where we use our chain rule. So we do know d of c with respect to p, because the carbon monoxide equation is measured using p as population as input. So we can get that. And then if we multiply that by derivative of population with respect to time, this will give us the change in carbon monoxide with respect to time. Okay, so we can now go back and look at these two equations. And so this first part is the derivative of this function with respect to p, and the second part is the derivative of this function with respect to t. Okay, so if we look at that as a function, so again, this we're going to have to use our chain rule for this one. So think of this as, I'll just write it out here, c of p. I'm going to change the square root just so I can think of it as more of an exponent. So 0.5 p squared plus 17 to the power 1/2. And this one's already written like that, so I don't really have to change it. So if I'm taking the derivative of this with respect to p, the 1/2 comes out front. And I've got my inside function, 0.5 p squared plus 17. And then the exponent, just like the last example here, gets reduced by 1, so that becomes negative 1/2. Okay. Now, since, taking the derivative of this, we have to use the chain rule. So we just did the outside function. Now we have to take the derivative of the inside function. So taking the derivative of this term, it would be 2 times 0.5, which is 1 times p to the power 1. So derivative of this is just p. Okay, so what we've got here, this is that part there. Okay, but we still have to take the derivative of p with respect to t. This one's a lot simpler because it's just a polynomial. So the derivative of 3.1 is just 0, and the derivative of this becomes 2 times 0.1t to the power 1, so that's 0.2t. So 0.2 times t. Okay, now if I was just asking for the derivative equation, I could do some simplifying here. I'd put this under a square root. Put this under the division line with this square root on the bottom. But I want to evaluate 3 years from now, so this is t equals 3. Okay, now have to be careful here, just like the last, well, a couple examples ago. I've actually got 2 variables in this derivative. I've got p and I've got t. So they're telling me that t equals 3. So I know what to put in for that. Okay, but what I do need to know is that when t is 3, what does that make? What does that make the population? So I plug in t equals 3 into this equation to get the population. So that would be t squared, that's 9, so 0.9 plus 3.1, that's 4. So that works out nicely. So basically I know the 2 inputs I need to use into this result. So I know d of carbon monoxide with respect to time, that's going to be equal to, and now I'm going to plug in my values here, 1/2 times 0.5 p squared, so that's 16, plus 17 to the negative 1/2, times, the p is 4 here, so I multiply that by 4, times 0.2 times t, so that's a 3. Sorry, I forgot my decimal here. 0.2 times 3 is 0.6. Okay, so it's just a matter now of simplifying this. So this will be 8, sorry, 1/2 of 16 is 8, plus 17 is 25. And so this is 1 over the square root of 25 is 1/5 times 1/2 times 2.4. That actually works out to be 0.24. Okay, so that was a fairly complicated looking problem. I'm going to finish this off with a word answer. Always good to read the question again to put the words right. At what rate will the carbon monoxide level be changing with respect to time? So therefore the carbon monoxide level will be, now since this is positive, that means it's increasing, so that's important. Will be increasing at the rate of 0.24. Now I need the units from this. So remember the units for the carbon monoxide, that's parts per million. So ppm, we could just keep that the same. And when does this happen? 3 years from now. So in 3 years from now. Okay, so this is a pretty good question because you've got two things that seem to be not related to each other, like the carbon monoxide level with respect to population and the population with respect to time. How can we put those two functions together? Well, that's through the composite function, and if we take the derivative of that composite function, we'll get the rate of change, instantaneous rate of change in 3 years from now. If we plug in t equals 3, which causes p to be 4. So this is a good question. I know in the past in unit tests we've had something similar with a word problem with two different functions that when combined they make a fairly interesting composite function. Okay, so I got some homework questions here to try. And this week's assignment will be based on these 3 lessons that we've done this week. And next week we'll be extending into more techniques and rules for derivatives. We'll be using the product rule when two functions are multiplying together, and the quotient rule when you have two functions dividing. Okay, so hopefully that makes sense to you. If not, please go on to YouTube and maybe search for videos on the chain rule or derivative of composite function. Okay, have a good day.